Today, our speaker today is Bob Tarjan. Bob is a professor at Princeton University, where I got my PhD. And I, of course, need to tell some kind of a story of when I was a little grad student. And Princeton had these evil, hard general exams. But the hardest questions, the ones that we feared the most, were the ones that came from Bob. If it involved amortized analysis, and it was complicated and twisted, you knew it came from Bob. So, the man who I feared the most as a grad student is now a colleague coming to give us a great talk. So, with that, Bob Tarjan.
It has never been my objective to instill fear into students. But I do love amortized analysis. It's a real treat to be here today. I haven't been to Rice for maybe 20 years. I flew down from New Jersey where it was pouring rain. We got a respite from the beautiful fall. What I want to talk with you today about is some work I've been doing with an undergraduate at Princeton, actually, Siddhartha Jayanti. We took a look at a classical problem which has a beautiful sequential solution and asked, can we make it concurrent and can we say something about its efficiency? So here's an outline of the talk. The motivating application was actually computing strong components on huge graphs. I'll talk a bit about this. First, I want to present the problem itself, talk a bit about the application, look at the sequential solution to the problem, talk about the concurrency model, and then we'll get to previous work on our own results. Before I do that, let me just mention some key takeaways from this. So it seems to be the case that ideas and results from sequential algorithms can carry over to the concurrent setting, but one needs new ideas and the design space is different in interesting ways. And especially trying to get efficiency results is very difficult and challenging. And even though there's been a lot of work in this area, I think there's still plenty to do. I was at PODC, Principles of Distributed Computing, this year, and Faith Ellen gave a talk, survey talk, in which she mentioned this as an interesting possibility. So for all of you who are looking for interesting problems, here's a place to find some. Concurrency creates subtle complications. All right, so what is the disjoint set union problem? Very simple. We want to maintain a partition of a set of elements. Devise a data structure that supports creating singleton elements, testing whether two elements are in the same set or not, returning true if they are and false otherwise, and combining sets. That is, given two elements, if they are in different sets, put the sets together. So here's creation of a new element, C, in a singleton set. We want to unite the C and A sets. What happens? Back up. There's the C and A sets put together, and this is the answer to same set query A and B at this point. A and B are still in different sets. Now, if I put the two sets containing A and B together and ask the same question again, the answer is now true. So the important thing about this problem is that the sets are not fixed. If the sets were fixed, we would just label every element with the set containing it. We could solve all these same set problems in constant time. Simple. But when we want to do a sequence of these operations on the fly, online, things get a bit more interesting. This is kind of a minimal definition of the problem, and in applications, it's often useful to have some additional abilities, so let me mention a few. First of all, we could give sets values such as names or sizes or some other information. Then when we create a set, we want to assign it some value. And then we can have an operation that exposes the value. Find value of x would return the value of the set containing x. If we're using set names, this would be the name of the set, for example. When we put two sets together, we need to combine the values of the corresponding sets. So we assume that values can be combined using some kind of operation, which I've denoted here by plus. So if the values were names, the plus just chooses a name, and we could either pick the name of the x set or the name of the y set. If values are sizes, this would be normal sum, and we can imagine other applications. Another different kind of extension is to allow one to iterate over a set with an operation such as find set of x, which in this case returns all the elements that are in the same set as x. Now, this problem has a long history. The original applications had to do with compilation, in particular compiling common and equivalent statements in Fortran. Anybody remember Fortran? Yeah, us old guys and the scientific computing people and so on. Back in the days of computers, the first real computer I ever programmed on was the Bendix G15. It was a refrigerator-sized box that you fed a paper tape in. Had a drum memory with 2,000 memory locations or something. In the old days, memories were really small, and Fortran had mechanisms to allow one to overlap storage. So you could declare by means of a common statement two variables or many variables to refer to the same storage location. And by means of equivalent statements, one could allow arrays to overlap to share space. So the variable names or the array names correspond to elements, and the overlap corresponds to sets, and you can extend the solution to the disjoint set union problem to figure out how to handle these sorts of questions. And the goal in the compilers was to do things on the fly, which turned it into an online problem. When one came to one of these statements, one wanted to adjust the data structure to take the statement into account. It is also a data structure that one can use in minimum spanning tree algorithms, in particular in Kruskal's greedy algorithm for minimum spanning trees, in computing incremental connected components, in undirected graphs, in computing percolation, and in some more interesting applications, in particular finding dominators in flow graphs, a problem I don't want to define, but more especially in finding strong components in directed graphs. So the strong components problem, we're given a directed graph. We want to determine what sets of vertices are mutually reachable. So a strong component is a maximal set of mutually reachable vertices. Here we've got a directed graph. We get 4 strong components. The strong components can be totally ordered in a way such that every arc either stays within a component or runs from one component to another. Such an ordering is called a topological order. And the goal then is to compute the components and to find the topological order. There are 2 different ones in this particular graph because this component has to come last. Once we get into it, we can never leave. It's a black hole. Either of these components can be ordered first, and this one has to be ordered after both of these. Now, there's a classical algorithm for solving the strong components problem that I developed in 1972, and there have been various other algorithms related to it discovered since. I want to mention a particular algorithm which illustrates the connection between the disjoint set union problem and the strong components problem. So you can compute strong components using a data structure for disjoint sets, and the idea goes back to Princeton in 1968. We do a depth-first search. We start at any vertex and we start walking along a path. What can happen? We can't go on forever because the graph is finite, presumably. Either we hit a dead end. If we hit a dead end, that's a black hole. That's a vertex that's in a strong component all by itself. We remove that, we put it aside, we report it as a component. The other possibility is we can find an arc from the last vertex on our search path back to something that we've seen before. This gives us a cycle. We can then contract the cycle into a single super vertex and keep going. That's essentially Princeton's algorithm. If you can't leave your present super vertex, you pop that as a component. You can keep going. The path gets extended. If you find an arc back to a vertex or super vertex that you've seen before, everything on the path gets contracted together. It's easy to show that this algorithm works because contraction preserves strong components. It's easy to implement. We just need an implementation of depth-first search, and we use a disjoint set data structure to keep track of the components. And the components are listed in reverse topological order. Now, it turns out that this is not a general disjoint set data structure application because the unions are very specific. They have the stack-like behavior, right? Whenever we have an arc that goes, we've got a stack of components, tentative components, representing a path through the graph. Whenever we have an arc coming back into the stack, we collapse, we combine all the components on the path from the place we've reached up to the end. So the contractions, the unite operations have a stack-like behavior, and one can take advantage of this to do a special purpose implementation of the disjoint set part, and it kind of disappears, and then you get a purely linear time algorithm. This is all well and good, except what happens if we have some kind of huge graph that we want to find strong components in? So here's where the application comes in, and here's where I got started with the problem. I was consulting for Microsoft Research, and I talked to Leslie Lamport, who does model checking for program verification. And in model checking, one needs to test whether there are cycles in programs that contain certain bad patterns or certain good patterns. In order to do this, one has to compute strong components. And these are in huge, usually implicitly defined graphs. That is, one has a way to, given a vertex, find the successors, but the graph is not presented explicitly. So the graph is huge. There's a possibility to try to use parallelism to speed things up. And in this setting, that may even be necessary if one wants to solve these problems in a reasonable amount of time. Now, the trouble with the algorithm that I just described to you and all the algorithms that compute strong components in linear time sequentially is they all rely on depth-first search. Depth-first search is a one-at-a-time process. It's very sequential. The question is, can we come up with a different approach, say by using breadth-first search or something like that, to get a concurrent or parallel strong components algorithm. Now, if the disjoint set union problem is inherent in here, let's try to solve the simpler problem of disjoint set union. So that was the motivation for us to look at this problem. Now, let me remind you how the classical sequential disjoint set algorithm works. If you have taken an introductory data structures course, you will have seen this. If you haven't seen it, it's really beautiful. It's about the simplest tree-based algorithm I know of. And there's sufficient flexibility in the data structure to allow interesting heuristics to be used. So I will call this the compressed tree implementation of disjoint sets. We represent each set by a rooted tree whose nodes are the elements of the set, and each node has a pointer to its parent. That's it. Every node has one pointer. The root is special. The root is the set identifier. The tree shape is arbitrary, but we have one tree per set. So the only requirement is that the trees must correctly partition the elements of the various sets. And this is disjoint sets. Things get much more complicated if we allow sets to overlap. So disjoint sets. Now if we want to do our same set and unite operations, we'll define some auxiliary operations that facilitate this process. So let me define, first of all, the find operation, which returns the root of the tree containing a given node. So if I do a find on G, I would get B. If I do a find on any of these letters, I would get B, because there's only one tree in this picture. We do a find just by following parent pointers until we get to a node that points to itself. For convenience, I've made roots point to themselves here, but that's not critical. We could make the root have a node pointer if we wanted to. All right. And we need ways to put two trees together. I'll call that the link operation. So if I want to link two trees with roots X and Y, I just make one of them point to the other. I make X point to Y or Y point to X. Observe that link is a constant time operation, but the find operation depends upon the length of the path from the given node to the root of its tree. Now I can implement the external operations very simply. To make a new singleton set, I just make the node point to itself. To implement same set, I find each of the elements. That gives me two roots, and I ask if they're the same or not. If they're the same, I return true. If not, I return false. To unite two sets, or two sets containing two given elements, I find the roots of the corresponding trees, and I make one point to the other. Any of these operations, except for the initialization, the make set operation, takes constant time plus two finds. Now, in talking about running times, I'm going to use n to denote the total number of elements, and we'll assume that that's fixed and all the make set operations are done first. So we got a fixed collection of elements. And we'll use m to denote the number of set operations arbitrarily intermixed on one. The number of links is at most n minus 1 because we start out with n elements, n sets, and we always have to have at least one set. We'll assume that we have at least two elements just for simplicity in stating time bounds, and that we got essentially a constant n number of operations, at least. That is, if there are elements that are never found, we can just ignore them. So essentially n can be taken to be a smaller value. That's what this means. All right, now of course this data structure has bad behavior unless we add some heuristics to it, because we can build a very long path by doing a sequence of links that always, okay, let's say this is the bottom. We build up a long path, we add a new root, singleton node at the top, we just keep building a long path. We can do long finds, linear time per find, that's very unpleasant. Our goal then is to reduce the time per find by keeping the depths of our trees small. And what we're really interested in here is the total time of a long sequence of operations, not just the individual time per operation. That's what I mean by amortized here, for those of you who don't know the word. So we can do this in two different ways. What we have is a rich design space because we can arbitrarily change the tree structure to squash the trees, for example, as long as the trees observe the correct partition of the nodes. So we'll look at ways to do this both in the linking and in the finding. So we have the freedom when we have two roots to make one point to the other or the other one point to the one. We'll use a rule here. Here are three rules. Linking by size, which was the first one invented, just says make the root of the smaller tree point to the root of the larger tree. Break a tie arbitrarily. This has good behavior. A related rule is linking by rank. Now, linking by size has an indirect effect on the maximum path length. It guarantees logarithmic instead of linear maximum path length, but it does it by keeping track of size. It's not actually keeping track of path lengths. The linking by rank rule is more closely tied to actually trying to minimize path lengths. So here's the way it works. You give each singleton node at the beginning a rank of 0. The rank is going to be a proxy for the depth, the maximum path. Whenever we link two roots together, we make the smaller rank root point to the larger rank. If there's a tie, we increase the rank of one of them by 1 and make the pointer go in that direction. Now here's another one that has only been studied recently. These are classical heuristics that date back maybe 30, 40 years. Here's a sort of an obvious one that uses randomization, which is the following. Let's number the elements at the beginning arbitrarily from 1 to n. Apply an arbitrary permutation, uniformly selected. And then, whenever we do a link, we make the smaller node with respect to this numbering point to the larger node. This is a randomized algorithm. All right, so we got three interesting linking rules, and we'll see that they all have the same effect. Essentially, they reduce the maximum path length from linear to logarithmic. The randomized rule, this is in expectation, is actually with high probability. Here we get the result deterministically. So these rules by themselves reduce the time per set operation from linear to logarithmic. We can also do something else, however. When we do a find, we can squash the find path. I'll call that compaction. Compaction is a general term. Here are two different ways of doing compaction. The classical one is path compression, where when we do a find, we walk up the path to the root, we make every node on the path point directly to the root. This is a two-pass method because we have to walk up the path. Here's an illustration. We do a compression of this path, we have to walk up to the top to find the root, and then only then can we change all these pointers to point to the root. That's compression. So if one wants a one-pass method, here's a method that does less compression, but it only takes one path, and it turns out that the theoretical behavior is just as good to within a constant factor as compression. Walk up the path and make every node point to its grandparent as one walks up the path. I'll call that splitting because the effect is to split the find path into two equal length halves. So here again is compression. Here is splitting of the same path. Right, so I take 2 steps up to 5, and then I make one point to its grandparent 5. I take one more step up to 8, and I make 2 point to 8. Take one more step to 10 and make 5 point to 10. And you will see here that this original path has got split into 2 more or less equal length halves. All right, so summarizing, here's the original. Here's what happens after compression. Here's what happens after splitting. There could be arbitrary subtrees dangling off of these nodes that I didn't draw, and they would just be still dangling. Okay. Now, what do we know about the running time of these various methods? I've actually defined 6 different algorithms here because we can use either compression or splitting, or actually 9 algorithms because we don't have to do any kind of compression at all. But if we use compression or splitting with naive linking, so I mentioned that any of the good linking strategies reduce the time per find to logarithmic. This is more or less what happens if you use a good compaction strategy with a naive linking strategy. You get the same reduction per find. And the exact value, the base of the logarithm has to do with the ratio of finds to elements. So what happens is if you do more and more finds compared to the number of elements, the time per find drops slowly, and that's reflected in this base of the logarithm. But here's the really interesting result. If you combine a good path compression technique with any of these good linking techniques, you get a total running time for M operations, which is almost constant. It's M times alpha of something, number of elements in this, called the find density. This alpha function is a functional inverse of Ackermann's function. How many of you have seen this before? Okay, so this is an amazing thing somehow. The original conjecture about these algorithms, in particular compression with linking by rank, was that the time was constant per find. And there's a long history of tighter and tighter analyses of this algorithm eventually resulted in this result, which is kind of amazing. So Ackermann's function was invented by Ackermann when people were originally studying computability theory and trying to come up with general definitions of what it means to be an algorithm. A Turing machine is one way to define algorithms. Another way is general recursive functions. Now, Ackermann invented his function to show that if you want to define functions recursively, you need more than single variable recursion. Primitive recursion does not suffice. This function essentially diagonalizes over all the primitive recursive functions, this A function. So there's a main value here and a secondary index. The 0th function is n plus 1. The first function turns out to be n plus 2. The way this works is the kth function iterates the k plus first function n times, essentially. So the 0th function is n plus 1. The first function is n plus 2. Not so interesting. The second function is something like 2n. The third function is something like 2 to the n. The fourth function is 2 to the 2 to the 2 to the 2, tower of 2's, n stacked up. The fifth function is even bigger. And alpha here is the inverse function, which as soon as k gets very big, this thing is growing hugely. This thing is very tiny. For all practical purposes, it's less than 4 anyway. Okay, so we've got this very simple data structure with this very simple process that's getting repeated. You can think of it, if you want to, as some kind of fractal behavior. We get very complicated outcome. Not only is this an upper bound, but it's also tight for the problem. There's no way to do better. So somehow inverse Ackermann function is inherent in the problem. That's the sequential algorithm. Simple data structure, hard to analyze. So let's turn to concurrency now. I want to look at the shared memory multiprocessor machine. Concurrent strong components, we were only able to find one paper in the literature, surprisingly, because this is a classical data structure, and you would think that more people had looked at the problem. Anderson and Wall did so in '94, and we'll use the same computer model that they did, which is a shared memory machine. In those days, it was known as an asynchronous PRAM. So we got a bunch of processors. We can assume each one has a local memory, and they access a common shared memory. We'll assume concurrent reads, but we'll synchronize the writes somehow. And the important point here is this is not a PRAM. These processors are operating independently and asynchronously, which is one of the things that makes this problem interesting and challenging. There can be arbitrarily delays between the operations, and the speed of the processors can be arbitrarily different. We'll assume that each set operation is done by one process, so several of them can run concurrently on different processes. One can imagine multiple processors assigned to the same operation, but the operations are so simple, maybe it doesn't make so much sense. All right. So we need a notion of correctness, and we need a notion of efficiency. So everything's operating concurrently. What does it mean to be correct? We'll use the notion of linearizability, which means that whatever happens, the outcomes, in this case, the answers to the same set of operations, are the same as if each operation is assigned some time, linearization time, during its execution, and its behavior is just as if it were executed instantaneously at its linearization point. To put it another way, every operation can be assigned some linearization time such that this is true. So there's a way to serialize things. And also, our goal is to avoid blocks, and the strongest property we can hope for is the wait-free property, where each process completes each of its operations in a bounded number of its own steps. So no process is waiting for any other process, and it's going to get done. Now, I get asked about this question, and I was already asked about it today. It's very difficult to get weight-free if we allow the universe to grow, because in this problem, if we have one process adding additional nodes, and another process trying to do a find, the find could never terminate because it runs right up the path. It can always make progress, but it may never reach the end. So the data structure, the algorithms I'll describe are weight-free if the universe is a fixed size, however large. And they are lock-free even if we allow make-set operations, an arbitrary number running on the fly. In systems applications, it makes sense for things to go on forever. In the motivating application, the strong component application, for example, the graph, however huge, is a fixed size. So talking about these algorithms as being weight-free makes sense. So here we have some operations running concurrently, and here are some linearization points, so that if these operations got executed instantaneously at their linearization points, the outcome of whatever concurrent processing is going on here is this union happened, is the same as if this union happened first, this union happened second. I don't know which one was this for, the same set. Okay. So this same set in this linearization gives the answer as of the time that these two got completed, but not this one. Another linearization would have this one completed first and then the same set done. So as long as there is some linearization, we're happy. efficiency. We're going to measure efficiency by the total number of steps taken by all processes as a worst case function of the problem parameters, number of elements, number of operations, number of processors. We could also look at the time per operation, and we're going to get a good bound for that as well, the number of steps per operation. Our goal here is that we want a total work bound. There's got to be more than, or at least as much as if one processor were doing all the work. We would like that it doesn't grow too fast with the number of processors. In particular, we'd like it to grow sublinearly in the number of processors, because then we're going to get some kind of speed up possible. Concurrency may help. If we get work that depends linearly on the number of processors, this is not a good situation. All right, now we need some kind of way to synchronize writes, and we want it to be block-free or wait-free, depending upon the situation. I use the classical, well, there are various synchronization primitives. This is the one we chose to use. It's a classical one. It's called compare and swap. It's a 3-parameter atomic operation, which I hope I got right here. So the idea is a process wants to assign value z to variable x. But it wants to make sure that x doesn't get changed in the meantime. So if the current value of x is equal to y, then the assignment happens and this thing returns true. Otherwise, it returns false. And this is an atomic operation. So the way this works is the process reads x, stores it in y, and then tries to do this operation. If no other process changes x before the CAS gets to complete, the assignment will be done. Otherwise, it fails. So this gives us a way to determine if we actually succeeded in updating a variable without having somebody else interfere, and it gives us a way to test interference. This is implemented in hardware on certain processing chips today. This is a double version of the same thing, where we simultaneously try to update 2 variables, x and u in this case, subject to the constraint that their current values are what we think they are. So this simultaneously updates x to be z and u to w, provided that the current value of x is y and the current value of u is b. Again, I emphasize these operations, if we use them, are supposed to be executed atomically. This one is not in any current hardware that I know of, although it was in the Motorola 68,000 I am told. So now I'm a sequential algorithms guy. I just got started with concurrent algorithms. This is the one that people accept as reasonable. This one, not so much. We'll come back to this point. Okay, now we're ready to talk about what Anderson and Ball did in '94. They attempted to implement a concurrent version of linking by rank with splitting using single compare and swap. As I'll try to illustrate in a picture in a moment, there are several problems with what they tried to do. The biggest one, or one of the biggest ones, was that single compare and swap doesn't seem powerful enough to implement linking by rank, because you need to control the rank of one node and the parent pointer of another node. Double compare and swap allows you to do this. So their algorithm is not able to avoid rank ties, which is what one needs to get all the nice bounds, the logarithmic worst case path length bound, the inverse Ackermann function bound. What they claimed for total work was something like this, which is inverse Ackermann function, tiny value times the number of operations plus the number of processors. So forget this. This is M times P. MP work. The work in the sequential case is just M. This work is growing linearly in the number of processors. That's bad all by itself. Even ignoring the fact this is not such a great bound, the analysis they did was buggy because they completely forgot to account for the interactions between different processors doing compression along overlapping paths, and this turns out to be to create difficulties. So we want to do better here. We would like to get simple algorithms with good work bound, sublinear and P if possible, and get valid proofs. So with compare and swap, it is possible to implement these path compression methods, in particular splitting using compare and swap, but as I mentioned, the analysis of Anderson and Wall is not correct. And link with compare and swap and ranks, that's a hard problem. So let's talk about this in more detail. I'm walking up my path here. I want to change the pointer at this node to point to this. I do a single compare and swap. I only have to change one value. I get to read this value and try to change it to this one. Now, I can do this. I can implement a version of splitting using a single compare and swap. But here's the problem of interfering processors. Let me see if I can describe this effectively. So here's the original path. Some process comes in, starts to read 1. It gets up to 5 here and decides it wants to change the pointer to 5, pointer from 1 to 5. But it stalls. Now some other process starts at 2, walks up here and puts in the red pointer. Now process 3 starts at 1. It goes 1, 2, 8, and wants to change the pointer from 1 to now point to 8, which is the new grandparent. However, this original process that was at 1 now wakes up and changes the pointer to 5. So process 3's CAS fails because this pointer gets changed to something in the middle here, which is worse than what would have happened had the process that we're interested in succeeded. And without going into the details of the analysis, this kills the analysis. We have to do something extra to deal with this situation. Okay, now with that in mind, let's turn to the other issue, which is the link operation. I want to put a new pointer in between 2 roots. If I'm doing linking by rank, or even worse, linking by size, if I'm doing linking by size, I have to update the size at this node and put this pointer in, and I have to do these 2 things simultaneously. If I'm doing linking by rank, it's the same thing, but I only have to change the rank here in the case which we hope is rare, where the 2 ranks here are equal. In any case, I cannot control the contents of these 2 nodes simultaneously without having something like a double CAS operation. On the other hand, if I'm happy with naive linking, things are okay because I can just stick this pointer in and it doesn't matter what happens at this node. In fact, this node could be a non-root by the time I actually succeed in putting this pointer in, and that does not create any problems. So let me, with all this preamble to set things up here, let me talk a bit about our results, which are still ongoing. First thing is the one I kind of hinted at. If you allow double CAS, DCAS, it's easy to implement linking by rank. And then you get either a weight-free implementation if you assume that the set of nodes is fixed or finite, or a lock-free implementation if you assume that it can run. Now, more interesting is what happens with splitting. So we have two versions of splitting with slightly different time bounds. It turns out that to overcome the interference completely, you need to do 2 tries on the cast before you give up and move on. And that's enough to give our best bound, which looks something like this. Per operation, the time is, there's an inverse Ackermann function determined here, but this is the more interesting thing. There's an additive log. It's essentially log p. So if you ignore the n over m issue, this is essentially m times a constant plus log p. So we've reduced the overhead because of the number of processors from linear to logarithmic. This has the potential to actually produce speed-ups in practice. Also, the maximum path length is always logarithmic, so another bound on the work, whether or not you do splitting or any kind of compression, is m times log n, which is independent of the number of processors. With a slightly simpler version of path compression, we get similar bounds, except there's a square up here in the number of processors, which is not so important because the log turns this into a constant factor, except in certain strange ranges of the ratio of m over n. But as I said, decast is not a realistic operation to use on modern machines. So can we overcome this? Can we use randomization or some other clever idea to overcome this problem? And again, the issue is if we want to do linking by rank, we want to put this pointer in here. If these two nodes have equal rank, we've got to change the rank here and put this pointer in simultaneously. On top of which, we got to make sure nobody else is changing this rank at the same time. And nobody else is changing the pointer, the parent pointer here at the same time. Otherwise, things go wrong. This is the difficulty that Anderson and Wall ran into. On the other hand, there's this other good linking by randomized index, which doesn't have this problem. We can do it by single cast. So this was actually the first result that we got. You can easily implement linking by random index with single cast. And now your results are average or with high probability. You get logarithmic time per operation. Depending upon the version of compression you use, you get the same bounds we've seen before. Which is nice. This is a simple algorithm. I think this one would be very effective in practice, but there's at least one theoretical difficulty. You need to make some kind of very strong independence assumption between the linearization and the randomization. So remember I said the way this works is you pick a uniform permutation of the items at the beginning, and then you use that as the indexing scheme. If the scheduler is malevolent and it knows the indexing scheme or can extract information about the indexing scheme from what is going on, the analysis here breaks down. So, nice result, but not totally happy. And anyway, we can still ask the question, is there a way to implement something like linking by rank with just single cast instead of double cast? All right, you've seen this picture many times. So here's our next result. Let me back up to this picture. So I said we got this problem. If these two nodes have equal rank, and I want to put this pointer in, and I'm trying to implement linking by rank, I got to change the rank here and put this pointer in and do these two things simultaneously. Instead of doing that, let's flip a coin, and if the coin comes up heads, we'll put this pointer in, or try to, and if the coin comes up tails, we'll change the rank of this node, increase the rank by 1, and try again. If we succeed putting in the pointer, we've linked the two trees. We may have two nodes of the same rank, which is not good, but half the time we're going to increase the rank of this node and then try to put the pointer in. And if we succeed that time, then everything is nice. This is another way to use randomization, but there's much less randomization going on. It's much more on the fly, and it's going to be much harder for the scheduler to exploit any knowledge it might have of the randomization. So I'll call this hybrid linking, and we get the same results that we've seen before for hybrid linking. Logarithmic worst case time per operation with this nice work bound or this work bound, depending upon exactly how we implement the splitting. So let me again say how this works. I want to link two roots, V and W. And the idea is to flip a fair coin to decide whether to try to put a pointer in or to increase one of the ranks. So here's some bit of code. To unite X and Y, we first do a find on X to locate the root of the tree containing it. Then we do a find on Y to locate the root of the tree containing it. We compute the two ranks just by looking them up. The ranks, so there's some, this is the easy part. If the ranks are different, we just try to put the pointer in the correct direction. Here's the interesting case. The two ranks are equal. And we flip a coin, which comes up, let's say, true or false. If it's true, let me not try to, if it's true, we try to change the values in vertex V. And this preserves the rank and puts in the pointer. This one preserves the pointer, keeps this a root, but increases the rank by 1. So I'm assuming now that this is a single cast, but it's operating on a pair of values, which I'm assuming I can store in double precision, or I can pack into a single word or something like that. I'll talk about how to get rid of this restriction in a minute. If the flip was heads and we put the pointer in this cast actually succeeded, we know the link was done, otherwise we've got to start over. So, reasonably straightforward. Let me say a few words about how the analysis works and where this log factor comes in. With linking by rank, or with linking by random index, we can use the sequential results to show that the tree depth is logarithmic. So this part follows immediately from the sequential results. To get the work bound with this funny log factor, we could find, again, we could call this the find density, if you will, which is M over N, but it's got a P or a P squared in it. And the idea is the following. Not only do these trees that get built have low depth, logarithmic depth, but most of the tree is low depth. So if we go K levels up from the bottom, the number of nodes drops down exponentially in K. So there's the top part of the tree that can be fairly deep, but there's not too much of it. There's the bottom part of the tree that's very shallow. So the log P terms comes from the shallow part. We just charge the fines against the processors, basically. We charge the steps taken by the processors against the individual fines up to a depth which is roughly log P. Then we apply the sequential analysis to the top part of the tree, which is a whole lot smaller. And now we got to multiply by the number of processors because they can interfere with each other. Either P or P squared per node in the top part of the tree in the sequential analysis, depending upon whether we're doing one try or the two try scheme. That's very roughly the idea of the analysis. The details are interesting and a bit subtle, but it all seems to be sound. And for the two-try method, at least for the algorithms I described, the bound is tight. I don't know if the bound is tight for the one-try method. I think we got the right bound for the problem, but we don't have a proof of that either. Now let me mention just a few more results. First of all, there's this issue that maybe you can't pack the rank and the parent of a node into one word, and maybe CAS doesn't support double word updates. Then you can play a sort of a standard game. There are a couple of ways to do it, where you use either a level of indirection or some kind of word sharing. And then you can use only single word CASs to implement this hybrid linking scheme. Cost you a constant factor, but that's okay. And if you're willing to do this word sharing business, you can also extend all of these algorithms to handle these extensions I mentioned previously, supporting values on sets, supporting iteration over sets, and other things. You have to do updating of values for the pointers that are supporting iteration every time you do a link. And there's a 4-step process that we worked out to do this. Now, we've got linking by rank with double CAS. We've got this hybrid linking by rank randomized strategy. There still is the question, can you implement linking by rank with single CAS? And actually, in Anderson and Wall's paper, they said we'll allow randomized algorithms, but then the scheduler has to know about the randomization. None of our schemes satisfy that, although the hybrid scheme, as long as the coin tosses occur after the schedule decides what to do, everything goes through. However, as a theoretical matter, it turns out you can actually use a technique that dates back to the PRAN days. Whoops, Cole, Michigan, 1986. Wrote a beautiful paper on something called deterministic coin toss. You get rid of the randomization. You can basically break the rank ties using this idea directly. You get a rather complicated algorithm, but it's completely deterministic. It uses only single CAS. It has the same bounds I've already mentioned. So from a theoretical point of view, we've now addressed the open problem that Anderson and Wall posed, or finished the job that they tried to do back in 1994. They actually mentioned this deterministic coin tossing idea, but they threw it in its full glory, and they then tried to put on top of it a general simulation of a PRAM by an asynchronous PRAM, and their bound isn't very good, and furthermore, it's very sketchy, and there are no details. And, however, if one takes the simplest version of this idea and applies it directly, one gets a much simpler construction with a much better bound, as it turns out. So I think we've done a lot of work on this problem, but we've only scratched the surface in terms of concurrent data structures and algorithms. Here are a few additional questions. Is the bound that we got tight, the word bound tight for the problem? I think the answer is yes. I think the log factor, log P, has to be there. I haven't yet seen a convincing argument, although I've had some experts in the world of concurrent processing suggest some ideas. I want to go back and look at the concurrent strong components problem and some of these data structures in mind. And I think there are other concurrent data structures that deserve further study, such as binary search trees, skipped lists, and possibly many others. So I'm excited about looking at some of these problems, and thank you very much for your time. I'll be happy to take questions. Question? No question?
Yeah, feel free to yell out. We're not doing anything fancy. Go ahead.
So how does the runtime, if you want to look at the distribution instead of just expected worst case upper bounds, so instead of expectation, if you want to look at distribution, any kind of ideas about it? So how does the complexity analysis go if I want to look at the distribution of the work instead of just looking at the expected work done?
For the randomized algorithms, all the bounds actually are high probability, I think, because what's going on underneath is some kind of negative binomial distribution. So you can apply Chernoff bounds to get very good behaviors. The variance is very low.
So you talked about working with large graphs, and people have looked at out-of-core algorithms, algorithms of memory hierarchies. Do you have any ideas to how the complexity analysis would work if you were really thinking of a large graph, but you want to take either of those techniques, out-of-core or hierarchical memory?
That's a very good question. I'd love to look at it. I haven't had time yet. I have no ideas at the moment. I think it's important.
So most of the time you spend talking about CAS and compare and swap. Do you think hardware transactional memory as an efficient support for synchronization would also be something more you could explore? You could open more opportunities?
Yes. It's more general, yes, so you can certainly do much more with it. The issue is the trade-off between generality and efficiency. If you can support it efficiently, it's a beautiful way to do many of these things. So here the natural thing is you need control over two values, two different locations at the same time. With binary search trees, if you want to start doing rotations and stuff, you need control over three values to do it in the most natural way. You need a triple CAS. And I'm sure there are settings where you need more, but the question is, can you build something that works efficiently? Or if you simulate it in software, the problem is the efficiency results vanish.
Other questions? Okay, I've got a question. So let's say that we've got a non-uniform distribution of queries, where the queries might be biased in favor of some subset of the nodes.
Yes.
What does that do to the analysis?
For this problem, as far as I know, nobody's ever looked at it. It could be a good question. Other than, well, for certain kinds of graphs,